Thank you. Thank you very much. I just want us to discuss in this lesson a small bit of trigonometric ratios, an interesting area in the field of mathematics. These trigonometric ratios, some of the time they're going to enable us to prove some of the trigonometric identities later on, but I wanted us to, on a quick note, look at some of these ratios that we have come across, and some of them may be new to us. Now, remember this, that most of these trigonometric ratios are related to the sides of a right angle triangle. And I've given a right angle triangle here relative to this angle theta, where I've said theta, relative to theta, this side is opposite, and this side is adjacent, and then the longer side is hypotenuse. Now, from the early discussion, we already know that sine of any angle is opposite of a hypotenuse. At the same time, the cosine is adjacent of a hypotenuse, and the tangent is also opposite of a adjacent. Now, from this relation, I've tried now to take so that we can come up with an easy formula to remember this. I've tried to take S from here, O and H to make this soccer, then C and A and H to make car, and then T and O and A to make tour. So the soccer tour will actually be enabling us to remember how to relate those trigonometric ratios. That sine is opposite hypotenuse, cosine is adjacent hypotenuse, and the tangent is opposite of adjacent. It's quite also important to note that from this relation, that tan theta is also sine over cos. It can be easily proven from this relation here. Are you together? Now, if I was to cross multiply here, making sine the subject, I also get another ratio which says that sine is the same as cos of cos multiplied by the tangent. That's another ratio, and for this case I can number them. Now this is our first ratio, the second one, the third one, the fourth one, and then the fifth one. Now again, I've given you a triangle on a Cartesian plane relating this one. There's an angle here, and I've said let the hypotenuse be r. Now using this hypotenuse, we can actually be able to relate this other side using those ratios. For example, if I was to demonstrate on a quick note that we know that sine of this theta will be the opposite, which is line AB over the hypotenuse, which is r. Now, if I was to make this AB the subject, I'll cross multiply to have AB equals to r sine theta. Therefore, I've tried to substitute this side with r sine theta. The same thing can be done here by relating cos of this angle to adjacent and hypotenuse, so that you can write this side in terms of r cos theta. Then, trying to apply the Pythagoras theorem, we know that the A, the B, then can relate to this C. If I was to call this one A, B, and C, then I'll say A squared plus B squared should equals to C squared, which I've done at this point, then substituted the value. You can realize that it really comes to r squared sine squared theta plus r squared cos squared theta is equals to r squared. Then on this side, I divided by r squared on both sides, and we ended up with this trigonometric identity, that is cos squared theta plus sine squared theta is equals to 1. This relation, or this identity, is actually true for any angle theta for that case. Now, from this identity, I've tried to make cos squared the subject by taking sine to the other side, which now goes to that cos squared can be written as 1 minus sine squared theta. Now, from here, you can actually factorize this one by use of the difference of two squares, and you can also note that cos squared can also be written as 1 minus sine theta, 1 plus sine theta. Or we can also decide to make sine the subject by taking cos to the other side, and this also gives us 1 minus cos squared theta. And also using the difference of two squares, we can also see that sin squared theta equals to 1 minus cos theta, then 1 plus cos theta for that case. But I want you to remember a point here, that sine squared theta plus cos squared theta is always 1. If you divide all through by sine squared, then it means it goes to 1. Then this one is cos squared theta. Sine squared theta is equals to 1 over sine squared theta. Remember, this one goes to 1 over tan squared theta, and a reciprocal of tan squared, because we know sine over cos is tan. Therefore, the other way around becomes the reciprocal, then is equals to 1 over sine squared theta. So we can actually again have an identity of this format. Similarly, if we have cos squared theta plus sine squared theta equals to 1, and I decide to divide by cos squared both sides or across, then we'll again end up with 1, then sine squared theta plus over cos squared theta equals to 1 over cos squared theta. Remember, if sine over cos is tan, then sine squared over cos squared is actually going to be tan squared theta. Then we are going to end up with this other identity, which is 1 plus tan squared theta is equals to 1 over cos squared theta. Then we can proceed on by a point of note here that in the subsequent video is that we can therefore use this discussed ratio to prove some of the identity, as we are going to see in the forthcoming videos. Remember, 1 over cos squared can be giving us another type of ratio, but for this level of ours, let it remain at that particular point. So follow me for the subsequent video for more proof of those trigonometric identity. I believe that this short video has enabled you to understand more on this trigonometric ratio. Be blessed and follow me for the forthcoming videos. Thank you.